Maybe you've heard of Hoover Dam or the Roman Colosseum, great feats of engineering whose main material is concrete, and they use this for its great strength and durability. In fact, that's why most of the world's modern infrastructure also uses concrete at its base. What most people may not know is that concrete needs careful nurturing to acquire the strength. That's why our research is on the effective curing on the flexural strength of concrete. My name is Ruben Romano.
My name is Tanim Chowdhury.
And we're from Warren Lab.
First, we'll go over our table of contents covering what we're going to talk about in this presentation. First, we'll talk about our background information. After that, we'll talk about our problem statement and hypothesis. Then we'll talk about our experimental processes. After that, we'll talk about our data, observations, and analysis. Then we'll make our concluding statements and talk about our takeaways and future research.
So first, what is concrete? So a concrete is a mix of four main materials: water, cement, fine aggregate, and large aggregates. Aggregates are things such as sand and gravel, and when the water and cement are mixed, they form a binding agent, which combines with the aggregates to form the basic structure of concrete. But how does the binding agent do this? So when we look at the binding agent, as we said, it's made of water and cement. There's two main chemical compounds in the cement which are required, which in our experiment used Portland cement, which is tricalcium silicate and dicalcium silicate. When mixed with the water, they undergo a chemical reaction known as hydration reaction, which produces two more chemical products: calcium hydroxide and calcium silicate hydrate. What this does is this fills the internal structure of the concrete, which the bulk of cement paste fills most of the air gaps, and the space between the aggregates and the cement paste, aggregates being the sand and gravel, known as the interfacial transition zone, or the ITZ, is slowly filled by the chemicals produced from this reaction. In the beginning, this initial structure is made by the tricalcium silicate, mostly its chemical reactions, but later on, this is mostly done by the dicalcium silicate. And it too, when mixed with water, produces the same binding agents. But at some point, the water runs out or is all used up. So this is where the main chemical process in this research comes into play, known as curing, which is the addition of external water to concrete, which continues its chemical reactions in its internal structure to allow for the development of that internal microstructure. And this is important because that internal microstructure affects a property of the concrete known as the flexural strength, which is the amount of stress the concrete can resist before deforming, measured in megapascals. In this experiment, we measured the flexural strength using a 3-point flexural test, which forced us to put our concrete into a beam-shaped format and then put it into a test machine, where two support pins would hold the beam at either end, applying normal force upward, while we applied an external force to the midpoint of the beam until the concrete broke. The flexural strength in this test was dependent on a couple of factors: the amount of force withstood, the depth of the beam, the width of the beam, as well as the distance between the supports of the test. But since the latter three are just experimental concepts we decide, the only thing that matters is that force withstood. And the amount of force withstood is ultimately dependent on the amount of stress the beam can resist before breaking. In the test, there are four main types of mechanical stresses the concrete will experience. The first being compression, when you squeeze a material. Next being tension, when you pull a material apart. Third being shear, when you apply a perpendicular force to the concrete beam, causing external microsoft layers to slide and pull apart. And so in the text, when the external force is applied, the concrete will experience all three: compression in its top half, tension in its bottom half, and shear throughout, combining to make the ultimate fourth stress known as bending. And so this is what ultimately causes the beam to fail. So whatever has the greatest resistance to the stress of bending will have a greater force withstood and thus flexural strength. And the stress resistance is determined by the internal microstructure of the concrete. This is because when you have a well-developed microstructure, as there's been a lot of chemical reactions with fillet, the microstructure is dense, so when force is applied, the force can evenly disperse throughout, allowing less concentrated stress and thus more force withstood before breaking, thus a greater flexural strength. When there's a less developed microstructure, meaning there's been very little chemical reactions, the force has less paths to travel through, so it builds up, allowing stress to concentrate, forcing the beam to break earlier, leading to less stress withstood and thus a lesser flexural strength. This means the flexural strength of concrete is heavily dependent on that internal structure, which is dependent on to be developed through chemical reactions that can be sped up through the development of curing.
Next, we'll talk about our problem statement for our experiment. Problem statement asks us to determine if there was a difference in flexural strength between cured and uncured concrete. Our hypothesis, meanwhile, stated that there would be a difference and that cured concrete would have a greater flexural strength. Next, we'll talk about our materials for making the concrete. First, we have our materials for the main mixture: gravel, sand, and cement. Then we have our materials for actually making the mixture: a garden rake and a concrete mix tub. as well as a graduated cylinder and a scale for measuring out our materials. After that, we of course have our beam molds to put our mixture in. Then we have a massage gun and a trowel in order to settle and smooth our beams. Finally, we also have plastic tubs for the use of curing. Now we'll go over how we actually made our concrete. First, of course, we had to 3D model our molds, and once we 3D modeled them, we 3D printed them using a flexible type of plastic. After that, we made our mixture first out of cement and sand, then we added gravel, then we added water. After our mixture was fully formed, we poured it into a mold, then used a massage gun to settle it, and then a trowel to smooth it out. 24 hours later, our concrete is dried, and we used a random sample, simple random sample, in order to assign treatments to each beam, 30 cured, 30 uncured. After that, we placed our 30 cured beams into a bin filled with water, and we placed the uncured beams into an empty bin, and we left them to relax for 7 days. Next, we'll go over materials for breaking the concrete. First, we have, of course, our concrete beam, which is held in place by a small U-bolt in the veneer materials tester. This U-bolt is connected to a force sensor by quick links and welded eye bolts, which, once the concrete beam is broken, the maximum force withstood will be measured by the veneer graphical analysis app on the laptop. Now, our experiment asks us to find flexural strength, but this setup finds force withstood. So in order to find flexural strength and force withstood, we use the following equation as well as the variables in constants in order to convert it. Next, we'll go for our procedure for actually breaking concrete. First thing we do is select our trowel, then we select an appropriate beam, cured or uncured, for putting it into the machine, making sure it's centered and tight. Then we slowly apply more and more force until the concrete beam eventually breaks. After that, we measure the maximum force withstood on the laptop and then put it into our Excel sheet where the formula for converting force withstood to flexural strength is applied. Next, after that, we'll go over some observations. As you can see here, we have a standard beam break, but most of our beams in reality actually showed major differences from this, such as having a off-center break, mold deformities, large aggregates, and other things. However, most of these observations were insignificant as they didn't really affect the values of our data, so we mostly put them aside. Next, we'll go over our box plot, which is a visual representation of our data measured. First, it's important to note that both box plots have a mostly normal distribution, although there is a outlier of 5.35 for the cured concrete, and this affects the ranges. This affects the range of the cured concrete, making it much larger and much closer to the uncured concrete in size. After that, of course, we have our means and medians. The mean of the cured concrete is slightly bigger than that of its median, which means there's a slight right skew, and while the reverse is true for the uncured concrete, where the mean is slightly less than the median and such as a slightly left skew. Finally, we can talk about the overlap between the box plots. As you'll see here, 50% of the cured concrete's data is above 75% of the uncured concrete's data, which suggests that cured concrete may indeed have a greater flexural strength. However, it's merely a trend, and in order to confirm this, we had to perform a 2-sample t-test. Now, in order to perform a 2-sample t-test, we need to meet 2 conditions. First, the large count/normality condition, which was met as we had 30 trials each for cured and uncured concrete. And then the randomization condition, which was also met because we randomly assigned our curing treatments when we cured them. Next, we'll go over our statistical hypotheses. Our null hypothesis states that the true mean flexural strength of the cured concrete would be equal to that of the uncured concrete, while our alternative hypothesis states that the true mean flexural strength of the cured concrete would be greater than that of the uncured concrete. Next, after we performed our t-test, we received the following results. As you can see here, our p-value is 0.0031 is less than that of our alpha level, 0.05, which suggests that there is a significant difference between cured and uncured concrete's flexural strength. Now, this leads us to our conclusion, which is that our null hypothesis, which once again stated that our true mean flexural strength of cured concrete would be equal to that of uncured concrete, was rejected. This is because, once more, our p-value is less than our alpha level. This provides convincing evidence for our alternative hypothesis, which states that the true mean difference in flexural strength between cured and uncured concrete would be greater than that of uncured concrete. This is because our p-value, which is 0.0031 or 0.31%, is the chance of having a difference in means be this extreme by chance alone. As it is less than our alpha level and also very close to 0, it's very unlikely for these results to be by chance alone. This leads us to accept or reject our hypothesis, and as stated previously, our hypothesis stated that cured concrete would have a greater flexural strength than that of uncured concrete, and our data shows that this is true. This is likely to be true.
So let's go back to the science to see why this happens. So as we said, the flexural strength is dependent on the amount of force withstood by the concrete, which is ultimately determined by the amount of stress it can resist, and that is determined by the density of the internal microstructure. And that microstructure can be developed through continued chemical reactions, which are prolonged through curing. Because when the internal microstructure is still filled with the binding agent produced by these chemical reactions, so that when a force is applied, the force can evenly disperse throughout the concrete as they concentrate in certain areas, allowing less stress to build up, thus more force withstood before the concrete breaks, leading us to say that curing does in fact lead to an increase in flexural strength. And past research also agrees with us. Past research by Francis Quessy and Humphrey Daniso, who investigated the compressive and flexural strength of concrete and the effect which curing had on this, especially multiple different types of curing, such as immersion cured, sheet covering, and water sprinkling, found that curing does lead to an increase in flexural strength. And not only that, but the curing which provides the greatest level of hydration had the biggest increase in flexural strength, as there was more water available to continue those chemical reactions, which developed the internal microstructure, leading to more stress resistance, more force withstood, and thus a greater flexural strength. Now, I'd like to go over some things for future research. The first being some fixes we would make. So, the first problem we encountered was with the molds. Initially, we used a harder plastic to make the 3D printed molds out of, which was impossible to remove the concrete beams out of. So later, once we moved to the flexible plastic, some of the beams did not come out perfectly as there were some problems with 3D printing. So this was caused deformities in the concrete beams when they were made. Additionally, another problem we encountered was with the treatments, as we had put the uncured concrete beams in a tub and then put a lid on top, but when we had closed this lid, water ended up building up and condensation caused the water to pool at the bottom, leading these uncured concrete beams to become somewhat cured in some areas as they were somewhat covered by water. So in the future, to fix these problems for the molds, we'd maybe try a different design, or maybe making them out of wood so they can be pulled apart and disassembled and maybe reused, which would hurt the concrete less. As well as for the treatments, maybe removing the lids, so making sure water doesn't build up and fill with water and actually cure them. Now, beyond these fixes, some areas for future research, we may be looking at different material ratios for the concrete, maybe different ratios of water and cement, as those greatly affect the properties of the concrete, as well as looking at different curing methods that we saw in that past research to see which is most efficient in developing the internal structure of the concrete. And beyond that, these changes of the features of concrete, also looking at things such as concrete reinforcement, which are much more used in the modern world to improve the properties of concrete, which it lacks, such as tensile strength and flexural strength, which rebar is used to improve it. Now, let's go to the implications. What did this whole research mean? So this research tells us that you should cure concrete to increase its durability and strength. And we've shown this at the microstructural and chemical level. This allows civil engineers and people in the construction field to build better roads, bridges, and foundations, as the concrete they use will be stronger for this, allowing overall better infrastructure for the world, and that will be less relying and stronger. With less strong infrastructure, it will be less money to upkeep. Now, I'd like to thank our contributors. Our first contributor was our professional contractor, John Barone, who was a U.S. Army Corps of Engineer who helped us with the science behind curing, as well as providing us with some help with designing our experiment. Next, I would like to thank our teachers, our math teacher, Mr. Moore, our stats and IES teacher, Ms. Sobolski, and our physics teacher, Mr. McMillan. I also like to thank our parents for helping us with this research as well with their support. That'll be all. Thank you. Any questions?